Okay, we're back. 3.4 Equations and Graphs of Polynomial Functions, Part 1. Okay, start up. Given f of x equals x to the fourth plus x to the third minus 10x squared minus 4x plus 24. A little bit of review. State the following characteristics. Degree and type of polynomial function. Degree is 4. This is a quartic. The end behavior of the graph. So remember this one. Degree of 4, that's key. Lead coefficient is positive. Okay, so I'm thinking of that, right? So remember I think y equals x to x squared. How does a parabola behave? Because that's also an even degree polynomial function with a positive lead coefficient. So it starts in quadrant 2, right? A parabola does this, right? Starts in quadrant 2, ends in quadrant 1. Starts in quadrant 2, ends in quadrant 1. Okay, always think of those close cousin polynomial functions. The zeros of the function. Okay, so you can actually, so just graph this on your graphing calculator. I get the zeros of -3, -2, and 2. If I sketch this function, what will it look like? Something like this. Okay, the y-intercept, y equals 24, so it's at 0, 24, right there. Okay, the interval or intervals where the function is positive, so the graph is above the x-axis. So we have our zeros laid out. It's positive for x is less than -3. Okay, and it's positive for x is greater than -2. So I'll highlight that. So where is it positive? Right there. And right there. Okay, the intervals where the function is negative, below the x-axis. So between -3 and -2, right? Remember, we don't want equal to 0, so I'm using the appropriate inequality signs. So right there. Okay, we will get into this later, but one thing you might have noticed is that this is a quartic. How many x-intercepts are there? I'm showing 3 x-intercepts. Okay, that leads me into part B here. Were there any multiple zeros with the same value? If so, did it affect the interval of the graph where it was positive or negative? Yes. Remember when we had this bounce thing, right? So here, I'm going to say bounce, not a technical math term, but we saw this in a previous lesson, this bounce thing. We talked about this bounce being tangent. Tangent meaning it touches but does not cross. So where did we talk about this bounce thing? Let me just look it up real quick. Sorry, folks. Bounce, bounce, bounce. Where did we talk about bounce? Sorry, bit of a segue here. know we talked about bounce somewhere. I'm going to find it just so you have a reference for what this bounce thing is. Is it here? Huh. I know we talked about it somewhere. Let me find it here. You could just fast forward. Sorry about that. I really do want to find it here. Oh, here we go. Bam. Bounce. Remember this? Right here, where the graph looks like it bounces off the x-axis. It doesn't cross, right? It's a point of tangency. We'll talk about that a little later, but remember this example if you kind of turn back in your notes. Okay, let's go back. We have a similar situation happening with this bouncing thing. So yes, multiple zeros at x equals 2, where the bounce happens. And yes, it affected the interval. Example, if the fourth zero were different, so if the fourth zero were x minus 4 instead of x minus 2, there would be an additional negative interval interval at 2 is less than x, but x is less than 4. What is the relationship between the zeros of the function, the x-intercepts of the corresponding graph, and the roots of the polynomial equation? They are, they all represent the same values. Okay, this part B, let me just sketch something out just so we understand. I don't want to leave it at just read the words and figure it out, okay? So remember, this is the original. Okay, we have this, and then it bounces, right? This is negative 3. This is negative 2, and then positive 2, right? And then so this one, the zeros are x equals negative 3, negative 2, 2, and 2. Remember, this is identical in real roots. So two identical real roots, I can list it as 2 and 2. If zeros were instead x equals negative 3, negative 2, 2, and 4, what would our graph look like? It wouldn't bounce anymore, right? So it would be like this, negative 3, negative 2, and then we have the 2, and then we have the 4, right? So it would look like this. No more bounce, and then it goes through like that. Okay, so in words, this part. Graphically, this is what I mean right here. Okay, hopefully that helps your understanding of that. Okay, let's go back. All right, here's this concept of multiplicity, okay? Multiplicity. If a polynomial has a factor of x minus a that is repeated n times, then x equals a is a zero of multiplicity n. The shape of a graph of a polynomial function close to a zero of x equals a, so the multiplicity of n, is similar to the shape of the graph of a function with degree equal to n of the form y equals x minus a to the n. The polynomial functions change sign at x-intercepts that correspond to odd multiplicity. So 3, 5, so 1, 3, 5, 7, 9. The graph crosses over the x-axis at these intercepts. The crossover point is the point of inflection. We'll go over what point of inflection means on the next page, but let me just get through this definition. Polynomial functions do not change signs at x-intercepts that correspond to even multiplicity. So 2, 4, 6, 8, on and on. The graph touches but does not cross the x-axis at these intercepts. The graph is tangent to the x-axis. So tangent, remember this is that bounce. Okay? And just to know it can either bounce up or down. So let me label these three graphs. 0 of multiplicity 1, right? That means for x equals a, we have three unique factors or three unique x-intercepts, right? There are no identical x-intercepts or no identical roots. So 1, 2, 3. Okay, so we can have something like -3, that looks like a 1, that looks like, let's say, a 5. So x plus 3, x minus 1, x minus 5. Okay, so that's a possible. So this would be a cubic. Okay, a 0 of multiplicity 2. Here's that tangent point. Let's call it a tangent point. I'm not going to use bounce because that's not a technical math term, but it's a point of tangency. So that's a tangent point. Tangent means where it just touches, it touches the x-axis but doesn't cross through it. We also have that point, right? This is a multiplicity of just 1. There's only one unique x-intercept, right? So if we say this is like -2 and this is, let's say, 4, how would we rewrite this polynomial in terms of its factors? X plus 2, there's only one of them, right? But this tangent point created at x equals 4, right? That would be x minus 4. And then there's a multiplicity of 2, so there's 2 of them. This is still a cubic, right? Let's investigate 0 multiplicity 3. Okay. Right there. Let's say that is 1. Oops. Okay. That's a multiplicity of 3. What does that mean? So the factor is x minus 1. That's the x-intercept. But it's a multiplicity of 3. So I put an exponent of 3. There's 3 of them. Okay. If you go ahead and graph this as y equals x minus 1 cubed, you'll get a cubic again. Okay, so these are the basic examples. So 0 of multiplicity 1. The graph passes straight through. Okay. Multiplicity of 2 or an even multiplicity. Okay. Graph is tangent to x-axis. Okay, and that's what we saw. And I should mention that these are for real zeros. Okay, at the very end, I think in next lesson, yeah, at the end of the next lesson, we'll go over what happens when we have non-real zeros. So this is also for real zeros. Okay, just to clarify. Okay, last one. Multiplicity of 3 or odd multiplicity. So 3, 5, 7, 9. Okay, well, I should mention even 2, 4, 6. Okay, what happens for a multiplicity of 3 or an odd multiplicity? Okay, graph has a point of inflection. Okay, so this point of tangency, point of inflection, remember this for when you take calculus, it will come up a lot. Okay, graph has a point of inflection on the x-axis. This is the point of inflection right here. Okay, on the next page, we'll define what point of tangency and point of inflection is. But when you have a point of tangency, think graph bounces. And it could bounce up or down. So if it's coming from the top, so in other words, if it's coming from the top, so it can do this. It can bounce up, or if it's coming from the bottom, it can bounce down. Okay, so that's the bounce thing, point of tangency. Point of inflection is when it changes from concave up to down or concave down to up. So, and I'll explain this with a nicer looking graph in the next page. Graph changes, and I'll define concavity. So it does something like this, right? So like that, or it can go the other way, like that. Okay? Let's go to the next page. I'll just define all this, but remember this discussion about what happens when the multiplicity is even or odd. Okay, next page at the top. Okay, tangent. A polynomial is tangent to the x-axis at a point where the graph touches the x-axis. It does not cross through it. So there we go. This is that bounce thing. Okay. And there we go. We can bounce the other way. So bounce, bounce. Okay. So this has to do with even multiplicity. Okay. Point of inflection. A polynomial graph has a point of inflection on the x-axis if the graph changes concavity. So concavity, think about a cup. If I leave a cup facing up, this is concave up. Concave up. If I turn the glass upside down, well, this is concave, you guessed it, concave down. Okay? A polynomial graph has a point of inflection on the x-axis if the graph changes concavity at a point on the x-axis. So at a point at the x-axis, at first the graph is concave down, so think about the downward facing cup, but then as soon as it hits the x-axis, it switches and goes concave up. Okay, same thing, it can go the other way. First it starts concave up, as soon as it hits the x-axis, concave down. And this has to do with zeros of odd multiplicity. even and odd multiplicities of a 0. So this is for a polynomial. The sum of the multiplicities, if you add up all the multiplicities of all the factors of a polynomial, the degree, it equals the degree of the polynomial. Okay? A real 0 of even multiplicity, so 2 or 4 or 6 or 8, occurs where the graph of a polynomial function is tangent to the x-axis. Tangent, that bounce. A real 0 of odd multiplicity greater than 1, so 3, 5, or 7, occurs, occurs where the graph of a polynomial function has a point of inflection, so think, is a cup up or is the cup down, has a point of inflection on the x-axis. Okay, let's take all of this, and then let's work on sketching graphs of polynomial functions from an equation. Okay? We're going to determine the following: the degree, sign of the leading coefficient, zeros and corresponding multiplicity, y-intercept, and behavior. So where does it start and where does it end? And intervals where f of x is positive or negative. Okay, we can do this. So example 1, sketch a graph of each polynomial function without using technology. Identify the characteristics of the polynomial functions. Okay. If we're sketching, it doesn't mean it has to be super exact, but we're going to get all the key points correct. Okay, so the degree, x to the third, x to the 1, okay, add those up, right, we get a degree of 4. And this is a quartic. Leading coefficient, right, so look at this x value, look at this x value. There's nothing in front of it, it's just a 1, so the coefficient's 1. And behavior. Remember, this is a 4th degree polynomial. What's its close cousin? Y equals x squared. The coefficient's positive, right? So what does a positive x squared do? Y equals x squared. Okay? It does this, remember, like that. So it starts quadrant 2, so like this, and ends in quadrant 1, like that. Okay? Because the LC is positive, and we have a degree of 4. Zeros and x-intercepts and multiplicities. So, first one, x equals 2. How many of those x equals 2 do we have? So identical real roots. We have 3 of them, so the multiplicity is 3. It's an odd multiplicity. So I'm going to put odd here. This will help us determine our shape. X equals -1. How many of them are there? There's just 1, so multiplicity is 1. Y-intercept. If I take that -2 and I cube it and multiply it by the 1, I get -8. So y-intercept is at 0, -8. Intervals where the function is positive or negative. Okay, let's graph this, then it'll help us visually see where this happens. Okay, so we said we have zeros at -1. So I'm going to do this for a little bit more scale. Every 2 ticks is a negative. Or sorry, every 2 ticks is 1. So -1, -2, -3, just so we spread it out a little more. So this is 1, 2, 3. Okay? And then on the y scale, it's just 1, 2, 3, 4, 5, 6, 7. So every tick mark is 1. So -1, -2, -3, and so on. Okay? All right, let's plot those zeros. So I have a 0 of 2. And I have a 0 of -1. Okay, so 2 and -1. We know it starts in quadrant 2. y-intercept of 0, -8, so -3, -4, -5, -6, -7, -8. Okay, so that's -8. So it starts in quadrant 1, or sorry, starts in quadrant 2. Okay, that 0 of -1, it has a multiplicity of 1, so it's just going to go straight through. Okay, something like that. Okay, and then it's going to come up. Oh, let me do a smooth curve here. Okay, and then it's going to come back up, and then the 0 that's at 2, it has a multiplicity of 3, so it's an odd multiplicity. It has a point of inflection, so it goes from concave down. So I'm coming from the bottom, so it's concave down. And then as soon as it hits the x-axis, it's going to shift to concave up. So my cup's turned upside down, and then now I'm turning the cup right side up. Okay, and this is accurately sketching a graph. So this helps us understand our intervals now. Interval where the function is positive or negative. So where is f of x greater than 0? Well, greater than 0 at x is less than -1, x is greater than 2. So I'll highlight that. Less than -1, greater than 2. And then where is f of x less than 0? Where is it negative? This is at -1 is less than x, and 2 is greater than x. Right here. Okay, there's your first sketching of a graph based on all the key characteristics. Okay, next one. G of x equals -2x cubed minus 11x squared minus 12x plus 9. Oh, man. Okay, we're not going to make it easy on you. We have to factor that, right? Remember, we're not using technology. So what do we do when we factor this? Okay, so I'm going to do this up here. So -3. Okay, remember the integral theorem, integral of 0 theorem. The 9, I'm going to choose all the various factors of 9 that could work. I'm going to simplify this for you. I found that -3 works, so I'm just going to do my synthetic division. Okay. And then let's factor this down into its components here. So okay, let's factor that. Okay, so g of x, what do we got? Equals -1 times 2x minus 1 times x plus 3 times x plus 3. Okay, that's factored form. Degree. Let's fill this chart in. 3. That's a cubic. Leading coefficient. Oh, what did I forget here? Oh, I see what I did. The leading coefficient here is, yeah, it's -2. Why is it -2? So if I can rewrite this part right off to the side, let's do that here. Okay, that's -1, 2x minus 1. That equals, if I factor out a 2, that becomes x minus 1/2. Oops, x. Yeah. Sorry about that. X minus 1/2. Okay, so if you multiply that out, okay, so the lead coefficient is -2. End behavior. I have a negative LC, lead coefficient, degree of 3. Think about our cousin here, y equals -x. Odd degree. What's the behavior, right? Odd degree. That's y equals -x. Think about that. That's how I think about end behavior. Well, it's going to start in quadrant 2. So like this. And it's going to end in quadrant 4. Like that. Okay? Zeros. X equals 1/2. So x equals 1/2. Multiplicity of 1. Okay, that's just going to pass straight through the x-axis. X equals, well, we have two identical real roots. X equals -3. Multiplicity is 2. And that's an even multiplicity. So what happens with an even multiplicity? Review time. Go back up. Even. Bounce. Tangent. Okay, so remember that for when we draw a graph. Y-intercept. This one, if all these are 0, so if g of x equals 0, then I get 9. Oops. Y equals 9. Okay, intervals where the function is positive or negative. I'm going to leave that alone until we actually graph it, then you can see it a lot better. Okay? All right, let's graph this. I'm going to go every 2 tick marks is 1. So 1, 2, 3, -1, -2, -3. On this, every tick mark is just 1. So 1, 2, 3, and so on. Okay, so -3, I'm going to plot my points. I have -3, and I have positive 1/2, so 1/2 right there. Okay, it starts in quadrant 2, and it ends in quadrant 4. This is a cubic, so it has that S shape. It's a negative LC, so that's why it starts in quadrant 2. Okay, so if it starts in quadrant 2, like this, for this x-intercept of -3, right? Even multiplicity, we know that's a point of tangency, so we're going to see it bounce. So it's going to go down, and then it's going to bounce, something like that. And then our y-intercept, 1, 2, 3, 4, 5, 6, 7, 8, 9, right there. It's going to bounce all the way up. It's going to come back down. And we know it has to finish and in quadrant 4. So we're on our way down here, on our way down, going to go straight through. No inflection, no bounce. Okay. So let's do the intervals. Intervals where the function is positive or negative. So f of x is greater than 0, and x is less than 1/2. Ooh, no, that's x is greater than 1/2. Sorry about that. Okay, so I'm going to highlight that. Oh man, sorry, wrong. Oh, let me start over. Okay. F of x is 0, so where is it positive? Sorry about that. X is less than 1/2, so that is correct. Okay. So right here, less than 1/2 is positive. Here's that bounce, positive. Okay. Where is f of x less than 0? Where is it negative? Well, x is greater than 1/2. Right there. So that's the positive, or sorry, that's the negative region, and that's the positive region. Okay. Next example. Example 2. Sketch a graph of a polynomial with the following characteristics. So now I'm going to give you the characteristics, and now you have to deduce or decide what is this graph going to look like. Okay? A fifth-degree function with a negative lead coefficient, and one of the zeros has a multiplicity of 3. Okay. So degree of 5, LC negative. Think about the cousin, okay? Y equals negative x. Just like y equals negative x, where does y equals negative x start and end? Y equals negative x does this, right? Okay, so let's start cataloging all the characteristics here. From just this information, I know that we start in quadrant 2 and we start in quadrant 2 and we end in quadrant 4. Okay, one of the zeros has a multiplicity of 3. Okay, and it doesn't say anything about the other ones, right? All right, but we need a degree of 5. So one of the zeros has a multiplicity of 3. So multiplicity of 3. So in terms of variables, x minus a to the third. Okay, what about the other two? Well, it doesn't say anything, so it's assumed that it's a multiplicity of 1. So x minus b and x minus a. So our function could look something like this. X minus a cubed times x minus b times x minus, oops, let me use c here so we're all different. Okay, just like that. So when we add these up, degree of 5. Okay, so I can say something like this. It has to start in quadrant 2, end in quadrant 4, and this is a quintic function, degree of 5. So my zeros could be here, C, B, and then let's say A is here. So what would this look like? Starts in quadrant 2, comes down, degree of multiplicity 1, so multiplicity of 1, it's going to pass straight through, and then pass straight through of B. It's going to come back around, and then concave up, and then change inflection, concave down. Okay. Multiplicity 3, there's an inflection. Multiplicity of 1, straight through. Multiplicity of 1. When I add up the multiplicities, 1 plus 1 plus 3, remember, our rule is that it matches the degree, so the degree is 5. Okay, and there's our sketch. All right, let's do part B, a quartic function. So degree of 4 with a positive lead coefficient and 2 zeros with a multiplicity of 2. Let's take care of quartic. and positive lead coefficient. So degree of 4, what's our cousin? So y equals x squared. Well, we know it looks like this. Okay, so it starts in quadrant 2. It ends in quadrant 1. Okay? 2 zeros with a multiplicity of 2. So this is multiplicity of 2. So that's x minus a. So this is an even multiplicity, right? So that's x minus a squared. And then the other one of multiplicity 2 is x minus b squared. Okay? So if I do a possible polynomial function in general form, it could be something like that. And this is a degree of 4. Okay, so if my zeros are here, b and a, it starts in quadrant 2, so like that, comes down. Okay, it's tangent, so it bounces off, comes back around, bounces off, and comes back around. Okay, multiplicity of 2. Multiplicity of 2. What did we say? 2 plus 2 equals 4, and that is our degree. So when you add up the multiplicities, they should equal the degree. Almost there. Example 3. Given the graph on the right, state the roots of the equation. The roots are all integral values. Okay? X equals -3, -1, and 2. So -3, -1, and 2. Algebraically determine a possible corresponding polynomial function. Okay? Let's check multiplicities. This is multiplicity. This is a point of tangency. So there's this bounce, right? The multiplicity for a tangency, right, possibly is 2. Okay? This is multiplicity of 1. Multiplicity of 1. Okay? At point of tangency, x equals 2, multiplicity is 2. So x minus 2 squared are the two factors. X equals -3 and x equals -1 each have a multiplicity of 1. So the factors are x plus 3 and x plus 1. Okay, so a possible, so I don't know what that lead coefficient is, right? We'll leave that alone, but I know my factors are x plus 3, x plus 1, and then x minus 2 squared when we put it all together, right? So this is going to be a quartic, 4th degree. Let's figure out this a value, right? I have a y-intercept at 6. Okay, so based on that y-intercept at 6, okay, let's algebraically determine the a value. So p of 0 equals, I'm going to use this equation, a times 0 plus 3 times 0 plus 1 times 0 minus 2 squared. P of 0 equals a times 3 times 1 times 4. So P of 0 we know is equal to 6. A times 12. So A equals 1 half. Okay, so in this equation we could rewrite it as P of x equals 1 half x plus 3 x plus 1 times x minus 2 squared. Okay, example 4. Determine the equation of a quintic function with zeros -2, multiplicity 2, -1, multiplicity 1, and 3, multiplicity 2, and a constant term of -9. Okay. Quintic, degree of 5. So let's look at x equals -2. Multiplicity of 2. So multiplicity of 2. That's x plus 2. The factors must be x plus 2 squared. Next one, x minus 1. Multiplicity of 1. So that's just x plus 1. X equals 3. Multiplicity of 2. That is x minus 3 squared. Add up the multiplicities. I have 5, which is my degree of 5. Okay, let's develop an equation. So P of x equals a, don't know what that is yet, x plus 2 squared. Let's multiply all the factors together. X plus 1 times x minus 3 squared. Okay, we know the constant value is -9, right? So that means P of 0 equals -9. So if I put in P of 0 equals a times 0 plus 2 squared times 0 plus 1 times 0 minus 3 squared. Let's put in 9 here for P of 0. And let's evaluate. And I have 1/4 equals a. Hang on a second. Constant value. Oh, sorry. Oh, my bad. Constant value is -9. Okay. All right. Let me just put some -9s here. So that should be -1/4. That makes sense because I'm starting in quadrant 2 and ending in quadrant 4. Okay. That makes more sense. Okay, sketch a graph of the function. So where does it start? Where does it end? So it's a degree of 5. I have a negative LC. So A is negative, right? So let me rewrite this. P of x equals -1/4 times x plus 2 squared plus x plus 1 times x minus 3 squared. I have a negative LC. That's -1/4. So think about my cousin, y equals -x. I have a similar odd degree function. Okay, so I know it's going to go like this. So it's going to start in quadrant 2 and it's going to end in quadrant 4. Okay, so let's sketch this. -2, -1. I have 3, and then I have a y-intercept of -9. Okay, so it's going to start in quadrant 2. And at negative 2, the multiplicity is even, so it's going to do this bounce thing. So it's going to do this. Oh, let me make a smooth curve. Sorry about that. Okay, bounce, come back around. Okay, at negative 1, multiplicity 1 is going to go straight through the x-axis with no inflection, just straight through. Okay, like that. And then it's going to pass through. Oh, curve sketching. Pass through negative 9. And then it's going to come around. And then at x equals 3, multiplicity of 2, it's going to do the bounce, but bounce down. Okay. Okay, let's take stock of this. So we've found the equation. So we got the equation right here, and then we've sketched the graph, right? So let me just finish with this. Okay, x equals negative 2. That's a multiplicity of 2. That's an even multiplicity, so I have a bounce or I have a point of tangency, right? X equals 1, multiplicity of 1 goes straight through the x-axis. X equals 3, I have a multiplicity of 2. That's an even multiplicity, so I have a point of tangency again, or that bounce. Okay, and that's it.